trapezoidal rule. So it is one of the method in the numerical integration. So we have the first problem here. We have the f of x is equals to negative 46 plus 45.4 x minus 13.8 x squared plus 1.71 x cubed minus 0.0729 x raised to 4 with the limit of from a we have 2 up to b we have 10. So by integrating this function, we can now arrive to the true value of, we have the true value of 58.62656. So in this method, we can see if it is closer to the true value or not. So first, we should know from the a, we should know the f of 2 by substituting the value of 2 to this function. So we can get the value of 2.1136. So for the second limit, we have f of 10. Again, substitute the value of 10 to this function. Therefore, we have the value of 9. So by having these two values, we can now substitute it to the formula of the trapezoidal rule. So we have the formula, we have b minus a, then quantity f of a plus f of b over 2. So by substituting these values, we have for b, we have 10 minus the a is 2 times the f of a is 2.1136. So we have 2.1136 plus the f of b is this, the f of 10. So we have 9 all over 2. So therefore, the value of this trapezoidal rule is 44.4544. So, by this value, we can get the true error of, by having this formula of true value minus the approximate value. So, we have 58.62656 minus this one, the value that we get from the formula. So, this one. So, we have the true error of 14.17216. So, which corresponds to a relative true error of, we have the true value minus the approximate value all over the true value times 100. So, 100%. So, we got the value of 24.17%. So, this means that it is close enough to the true value that we have. So, the second rule that we have is just the Simpson's rule. So, it is just the same with this. So, we can explain it like this. So, for the Simpson's rule, okay, so we have Simpson's rule. 1/3 rule, I mean. So, okay. So, it is just the same with the previous equation that we have. .0729 x raised to 4. So again, it has the same limits of this. So a while ago, we already find the value of the f of 2, 2.1136. Then for the f of 10, we have 9. So in Simpson's rule, we can find its another function by having b minus a. So with n of, we have two segments. So we have to divide it by 2. So we have 10 minus 2 all over 2. So we have the value of 4. So we need to find the value of f of 4. So again, by substituting the 4 into this equation, so we have the value of 5.5776. So again, the general formula for the Simpson's rule is b minus a, quantity of f of x sub 0 plus 4 times the f of x sub 1 plus f of x sub 2 all over 6. So by substituting these values into this equation, so we have 10 minus 2. So we have 10 minus 2. Then the f of x sub 0 is the 2, the f of 2. So we have the 2.1136 plus 4. So the f of x sub 1 is this one that we get from this equation. So plus 4 times 5.5776 plus, and the f of x sub 2 is the f of 10. So we have 9 all over 6. So by having this formula, we have arrived to the answer for the Simpson's 1/3 rule of 44.5653. So, based on the true value that we have before, so again, we can find the true error of PV minus AV. So again, we have the value of 14.06, which corresponds to a relative true error of 23.98%. So as you can see, Simpson's 1/3 rule is close enough to the true value that we have as we compare to the trapezoidal rule. So these two rules that we have discussed is just the two methods in the numerical integration. So that's all. Thank you. So our next topic is about divided difference. So we have three types of this. So we have the backward, the forward, and the central. So first, we should have a function. So for example, we have f of x of x raised to 5 minus 3.5 x raised to 4 plus 2.75 x raised to 3 plus 2.125 x squared minus 3.875 plus x plus 1.25. So we have a step size of 0.5 and the x sub 0 of 0.5 also. So to have this equation in the divided difference, so we should find first the first derivative of this function. So we have the first derivative is 5 x raised to 4. Then we can use the power rule. So we have negative 14 x cubed plus 8.25 x squared plus 4.25 x minus 3.875. So we can find the true value of the first derivative by integrating this one or by substituting the value of x to this. So we have the true value of this. So we get the value of 0.875. So later on, we will compare in which the three of this is closer to this true value. So for the forward divided difference, so we have the formula of f prime of x is equals to f of x I plus 1 minus f of x sub I all over the step size or the h. So in the forward divided difference, we can find the xi plus 1. So again, we have the x sub 0. So it serves as the xi or the x sub 0. So we have 0.5. So it means if we backward the step size, so we have the I minus 1 of or of 0. Then for the xi plus 1, since we have the step size of 0.5, so 0.5 plus 0.5, so we have the value of 1. So, since we have these values, we can now substitute those values to the original equation to find the f of xi minus 1 and the f of x sub I, then the f of x I plus 1. So, to substitute these values into this equation, so we arrive to the values of 1.25. Then for this one, we have 0. Then for the f of xi plus 1, so we have negative 0.25. So, therefore, we have all the values that we need to come up to this equation. So, for the f of xi plus 1, so we have negative 0.25 minus the f of x sub I, so we have 0. Again, the step size is 0.5. So, the f prime of x that we have for the forward divided difference is negative 0.5. Okay. So, for the backward divided difference, so the formula is f prime of x is equals to f of x of I minus f of x I minus 1 all over h. So again, substitute those values. So we have 0 minus 1.25 all over 0.5. So we have the value of negative 2.5 for the backward divided difference. And the last, we have the central divided difference. So we have the formula of this, f of xi plus 1 minus the f of xi minus 1 all over twice of the step size. So we have 2 times h. So by substituting those values, we have negative 0.25 minus 1.25 all over 2 times 0.5. So in the in the central divided difference, we arrived at the value of negative 1.5. So based on the values that we got from those different kind of divided difference, so the true value is this one. So as you can see, the closer value to this is something like the forward divided difference and the central divided difference. But it is close enough to the central divided difference. As you can see, it is 1.5 and the true value is negative 0.875. So that's all for this topic. So thank you. Okay, so our next topic is about the Euler's method. So we have an example of dy over dx is equals to y minus x squared plus 1. So we have the given of y of 0 that is equals to 0.5 and a step size of 1. So to get the value of y, we should find the f of 1. That is the requirement that we have to find. So if I is 0, so then the y of 0 is equals to 0.5, then the step size is 1, and any value of x could be, so we should set the x of 0 by 0. So the formula here is y I plus 1 is equals to y of I plus f of x sub I, then y times h, or the step size. So in this, so if we have the I of 0, so I plus 1 is just 1 equals to y of 0 plus, then this one f of x sub 0, then y of 0 times h. So by substituting these values into this equation, so we have y1 because the y0 is 0.5 plus, so in this, the x sub 0 and the y sub 0 should be substituted to the equation. So we have the y, 0.5, minus, so we have the x sub 0 squared, so plus 1, and the step size of 1, so times 1. Therefore, we have the value of y1 of 2. That is for the when I is 0. So, from the concept of divided difference a while ago, error can be reduced whenever the step size is also reduced. So, let's have an example. So, let's change the given. So, if h is 0.5, with the same procedure, so, again, we have the x of 0, then the y, it's just the same, but we just change the step size to prove that the error is reduced by reducing the step size. So again, if I is equals to 0, again, same procedure, y of I plus 1 plus f of x I 1 times h. So again, we have the y1, y sub 0 plus f of x sub 0, comma, y sub 0 times h. So we have the y sub 0, 0.5 plus, again, substitute the values, these values to the equation. So we have 0.5 minus 0 squared plus 1. And again, the step size is 0.5. So we have the value of 0.875. So as you can see, it is true that when we reduce the step size, the error is also reduced. So by comparing the true value to the approximate value. So that is all about the Euler's method. So thank you. So our next method is about Yun's method. So we have an example here. So dy over dx is equals to x plus y minus 1. So we have the given of y of 0 is equals to 2, then step size of 0.5. So here, so for the x, we have xi plus 1 that is equals to xi plus h. So here, we can assume that x sub I is 0. So we have a table here so that we can easily understand. So we have the predictor side. So the formula for this one is yi plus 1 is equals to yi plus plus h f of xi comma f of xy. So for the corrector side, we have yi plus 1, so is equals to yi plus h over 2, then quantity f of xi comma yi plus f of xi plus 1 comma yi plus 1 quantity. So for this, the y1, the y sub 0, I mean for I is 0, we have 2. So for the next table, we can now assume that x2 is equals to xi or 1 plus h is equals to the value of x1 is 0, so the h is 0.5. So the value of x2 is 1/2. So for the y2, here, when I is 1, we have yi or y1 plus h xi plus yi minus 1. So we have 2 plus the h is 0.5 or 1/2 times the xi is 0 plus 2 minus 1. So we have y2 of 2.75. So for the corrector side, it's just y2 is equals to y1 plus h of 2. Again, quantity x sub I plus yi minus 1 plus x sub 2 plus y2 minus 1. So, again, we can now substitute the values of 2 plus 0.5 divided by 2, then 0 for x sub I plus 2 minus 1 plus 1 half plus 2.5 minus 1. So again, for the y sub 2, we have the value of 2.75. So, as we continue the iteration up to different kind of segments, so we can um, get close enough to the true value that we want. So, in this case, we only iterate up to when I is 1. So, the answer here is this one. So, the y2 is equals to 2.75. So, okay, so the next one is the Ralston method. So, we have an example here. So, dy over dx is equals to 8 times e raised to negative x minus 3 sine y. So, again, we have the given of step size of 0.5, y sub 0 of 0.5. So, again, to implement this kind of method, so its general formula is this: yi plus 1 is equals to yi plus 1 over 3 k1 plus 2 over 3 k2 times the step size. So, again, when I is 0, we should find first the k1 and k2. So, for k1, we have the f of x sub 0 times y sub 0. So, we have, again, we should substitute the value of this x and y to the equation. So, we have 8 e raised to negative, again, the value of 0, x is 0, minus 3 sine times, and the y is 0.5. So, we have the value of 6.5617. So, that is for k1. So, for k2, we have f of x sub 0 plus 3/4 times h, comma, y sub 0 plus 3 over 4 times k1 times h. So, again, substitute the value. So, we have the x sub 0 is 0 plus 3 over 4, and the h is 0.5, comma, then 0.5 plus 3 over 4, the k1 is 6.5617 times the h of 0.5. So here, for the x, we have 0.375. Then for the y, we have 2.9606. So again, substitute these values. 8e raised to negative 0.375 minus 3 sine quantity 2.9606. So again, we have the value of 4.9583. So, again, we can now substitute those values to this general equation. So, we have when I is 0 again, we have y1 is equals to, the y0 is this one, so we have 0.5 plus 1/3. The value of k1 is 6.56 times 6.5617 plus 2/3, and the value of k2 is 4.9583 times the value of h is 0.5, so we have here. So again, the value of y1 is equals to 3.2464. So this is the value for the Ralston method. So our next topic is about the midpoint method. So again, we have the given of dy over dx is equals to y times x raised to 3 minus 1.5 y. Again, we have the given of y sub 0 is equals to 1, the h or the step size is 0.5, x sub 0 is 0. So, in this kind of method, the general formula is yi plus 1 is equals to yi plus k2 times h. So, again, we need to find the k1 in order to find the k2. So, for k1, we have f of x sub I, comma, y sub y. Or f of x sub 0 for I is 0, comma, y sub 0. So again, substitute the value of x and y to this equation. So we have 1 times 0 cubed minus 1.5 times 1. So the value of k1 is negative 1.5. So for the k2, we have f of x I plus 1 half h, comma, y of I plus 1 half k1 of h. So, here, we have f of x sub 0 plus 1 half h, comma, y of 0 plus 1 half k1 times h. So, again, substitute the value. So, we have 0 plus 1 half, and the value of h, or the step size, is 0.5. So, we have 0.5, comma, y sub 0 is 1 plus 1 half, and the value of k1 is negative 1.5. The h again is 0.5. So again, for k2, we have the f of, for the x, we have 0.25. Then for the y, we have 0.625. So again, substitute these values to the equation. So we have 0.625 times 0.25 cubed minus 1.5 times 0.625. So for the K2, we have the value of negative 0.9277. So now we have the value of K2. So we can now substitute these values to this general equation. So we have, if I is 0, then so we have y1 is equals to the y sub 0 is 1 plus the k2 is negative 0.9277, and the h is 0.5 times 0.5. Therefore, we have y1 that is equals to 0.5361. So this is the final answer for the midpoint method. Okay, so our next topic is about RK4 with the fourth order polynomial. So let's have an example here. So dy over dx is equals to y minus x squared plus 1. So we have the given of y of 0 is equals to 0.5 and a step size of 1. So we need to find the y of 1. Again, with the same questions a while ago with the Euler's method. So at I that is equals to 0, we have x sub 0 is equals to 0, then y sub 0 is equals to 0.5, then a step size of 1. So we have k1 is equals to f of x sub 0, then y sub 0. So in order to get the k1, we need to substitute the value of x sub 0 and y sub 0 to the equation. So we have 0.5 minus 0 squared plus 1. Therefore, we have the value of k1 of 1.5. So for k2, we have f of x sub 0 plus 1 half h, comma, y of 0 plus 1 half k1 times h. So again, substitute the value. So we have f, the x sub 0 is 0 plus 1 half times 1, comma, then for the y sub 0, we have 0.5 plus 1 half, then the value of k1 is 1.5, and the h is 1. So we have, for the x, we have the value of 0.5 and 1.25 for the y. Again, substitute these values to the equation. So we have 1.25 minus 0.5 squared plus 1. So the k2 will be 2. So, for K3, again, with the same formula, plus 1 half h, comma, y sub 0 plus 1 half K2 times h is equals to, again, 0 plus 1 half times 1, 0.5 plus 1 half, and the K2 is 2, then 1. So, the x will be 0.5, then the y is 1.5. So, again, substitute this value. So, we have 1.5 minus 0.5 squared plus 1. So, K3 is equals to 2.25. So, for the last one, we have K4. So, we have f x sub 0 plus h, comma, plus K3 times h. So, again, substitute. We have 0 plus 1, comma, then 0.5 plus 2.25 times 1. So, we have, for the x, we have 1, then 2.75 for the y. Again, substitute these values. So, we have 2.75 minus 1 squared plus 1. So, we have 2.75 for the K4. So, to obtain the y of this RK4 method, so we have the formula of this. Plus 1 over 6 K1 plus K2 plus 2K3 plus K4 times H. So, again, substitute. So, we have y1 plus the y sub 0 is the y sub 0 is 0.5. So, we have plus 1 over 6. The value of K1 is 1.5 times 2. The K2 is 2 plus 2 times K3 is 2.25 plus the K4 is 2.75 times 1. So, the value of y1 is equals to 2.625. So, this is the final answer for this method. So, thank you.